Okay, maybe I can. Okay, let's get started then. Okay, so this week in the seminar series, we're going to be talking about complete positivity. This is sort of a somewhat distinct direction from the last time. So let's get started. If you guys have questions, please try to speak them out verbally because I'm not able to check the chat at the same time. My apologies for that. So the first thing that I want to do is first, we've been talking about the pure state formalism, and in the beginning of the seminar series, I did not actually introduce notions like density matrices, but a complete description of quantum mechanics, or the most general one, is one in which we go from having vectors to density matrices, and instead of unitaries, we have in fact completely positive maps. I guess we could also add unitaries plus measurements. Sort of all of these are taken into account by completely positive maps. So just to sort of recap for people who haven't seen this sort of terminology before, we typically in the pure state formalism, we talk about vectors psi in some Hilbert space. They are normalized using the usual Hilbert space inner product, and probabilities for a particular measurement setup are given by the Born rule, which is this inner product squared. Now, we can make an interim sort of transition to the mixed state formalism by first recognizing that we lose no relevant physical information by going from psi to psi, this sort of cat-bra outer product. This projects onto the one-dimensional subspace spanned by psi. The normalization condition for using these matrices instead of the vectors is that the trace is equal to 1. The Born rule is given by taking the trace of this operator producted with some other state phi. So that's that. So the leap from here, this side of the picture, all the way to the mixed states is as follows. We have some density matrix rho. Well, what is a density matrix? It is some matrix, Hermitian, which has trace equal to 1, and it gives me something non-negative for every possible quantum state chi in the Hilbert space. And in particular, I can write rho as being the convex combination of some pure states. One moment, please. Okay, one moment. Okay, there we go. So let me make sure I'm okay. Okay, perfect. So that's the general sort of prescription. We're going from pure states, vectors, to these density matrices here. So just to give a little bit of background, because there's a sort of hierarchy of operators that we're going to be dealing with here. So a linear operator between two vector spaces, M is a linear map from V to W. The set of all possible linear maps from V to W is this curly L. And then if we have linear maps from V to V, the same vector space, then we just call this script L of V. Also, okay, that's not, I said it was useful. It's not that useful with the traces. We kind of know what that is. So here's a sort of depiction of the operators that we tend to deal with in quantum mechanics. You've got the normal operators such that you have A dagger equals A dagger A. That is, A commutes with its dagger. Below that is Hermitian, which satisfies A equals A dagger. So obviously that's also normal. For operators that are Hermitian, we call them positive if for some A mapping from, say, well, an operator P in L of V is positive if there exists some A going in maps from V to W such that P is equal to A dual A, like so. We call it then a density matrix if it additionally satisfies that the trace is equal to 1. So these are the rows that we had up here. Projectors are precisely those positive matrices operators that satisfy P squared equals P. And then it turns out to be the case that the pure states that we talked about all the way up here lie at the intersection of these two kinds of operators, densities and projectors. In particular, they are the density, from one point of view, they are the density operators that satisfy P squared equals P, or they are the projectors satisfying trace of P equals 1. Additionally, there's other sorts of matrices or operators, isometries, and also unitaries that we've talked about before. So, I mean, this stuff is not rocket science here. All that I want to sort of show you is that it's possible to see just from this normal picture how you get that if psi is a normalized vector, a normalized ket, then this thing will also be equal to 1. And we can also show how the Born rule, how the two definitions of the Born rule work out precisely the same, like this. Okay, so we can actually talk about operators on operators. So what do I mean here? I was going to use the term super operator, but that actually has a technical meaning that I was not aware of before. So let's just call these super duper operators. And what do I mean by that? These are maps, linear maps from the set of linear maps from V to V to the set of linear maps from W to W. And let's denote T of VW to be the set of all such maps from L of V to L of W. So there's a couple of special cases that we might be interested in. Phi, which is a super duper operator in my terminology, is Hermitian preserving if the image is Hermitian in W for every A in the domain. It's positive. There's a similar sort of notion that phi is positive is if the image is positive for everything in the domain. Completely positive is another term that we're going to be using, which is to say that phi is completely positive if this tensored map phi tensor identity, where the identity is on L of x for every x, which is just some Hilbert space. If that is positive, then we say that phi is completely positive. In addition to this, we could also talk about trace preserving maps, those where the trace of the image is equal to trace on the domain. And unital is one that preserves the identity. So this is more like an operator theoretic approach. So we can also introduce an abstract definition notion of these types of things. So what are we doing here in the procedure up top? Well, what we're kind of doing in this abstract framework is the following. We have a ket is something like a map from I to A. In some, usually we're dealing with a symmetric monoidal category. So we have that P, the composite map here, is actually positive Well, we will define precisely what it means to be positive later, but you can see that you'll see that this actually accords with that definition. It's a map from A to A. So this is like our psi. You can go from these maps, a dagger, to the name of that map, which is a map from I to a dual tensor with A. Kind of what you're doing here is you're actually talking about a preparation of a matrix is kind of what you're doing here. So that sort of, and then instead of talking about this pure state like this, we can equivalently talk about so-called positive matrices instead. And there's a particular formula for this in F-Hilb. Let's see if there's any questions. No. Okay. Okay, so more explicitly, a morphism is in a Dagger category is positive if there exists an object B in the category and a morphism between A and B, such that we have that either F is equal to G dagger G composed with G dagger. This is just the dagger of this equation over here. It's more general, obviously, but you can see that this equation here is also of this form. It's just related by the dagger. So it's positive, or diagrammatically, we can have that F is positive if it can be decomposed in this particular way. Of course, this decomposition is not unique. So to recall what this symbol was up here, let's recall what the actual name of a morphism is. So in a compact closed category, the name of a morphism from A to B, which we can write algebraically like so, can be given graphically as this cup shape, where F is precisely the morphism in question. So a positive matrix, so if we have a morphism F from A to A, which is perhaps like our P up here, something that could be positive. So a morphism, the name of F, where F is positive. So this will be called a positive matrix. And if B is equal to I, so that this is the identity, then the name of F is just called a pure state. In particular, so we actually want to build up this concept a little bit more. These positive matrices will eventually be tied to a Frobenius structure. So I just sort of want to recall some basic definitions from earlier in the seminar series. So we have this lemma back from chapter 4 of Vicary Heunen. If you have a monoidal category and has a duality A and A star, then there's a canonical monoid structure on the tensor A star tensor A, and this is the pair of pants. You can just construct this monoid, which is going to be something in principle that does this. And you also have something like this. So this is a canonical monoid structure. Corollary to that is that if you have a monoidal dagger category with a dual, then the monoid on then this monoid can actually be promoted to a Frobenius structure. That is, because we have the dagger, we can actually define a comonoid, and then also it's compatible with the monoid. Therefore, we have this Frobenius structure. So how do we get mixed states out of this? So we kind of had a nice definition for what a pure state looks like. So how do we get mixed states out of this? So let's see. We sort of have this sequence of shifts in perspective that we want to pursue. First is that you have a positive matrix M, so that you have a preparation from I to A star tensor A. And then we want to actually shift from this picture, which is the positive matrix, to maps from A star A to A star A. So when we shift this perspective, we have that we can have a diagram that looks like this. So instead of this, we actually have something like this now. And actually you can show that with the requisite structure that we have in our category, that actually we have this sort of picture. This sort of picture, though, is very reminiscent of something. So we're working here with pure states, actually. What we're trying to do is build up to the mixed state formalism by making a shift from just using this AA, or from psi in quantum mechanics, to some more general positive matrix M. So once you actually write down a graphical representation like this, you make this substitution M here for, instead of just AA, which is positive, to a generic positive M. And then you can sort of notice that that this is some object A star A, this is some object A star A, and what you actually have is a monoid, or actually even a Frobenius structure on objects of this type. So, in fact, in a monoidal Dagger category, a mixed state of a Frobenius structure B with the requisite sort of monoid, comonoid that interact is a morphism I from I to B, satisfying the following equation. This is just the same picture as up here, and it must be that this is equal to this, where we have basically the composition. You have that G goes from A to X, and G dagger goes from X to A. So this thing is positive. So we have that a mixed state is precisely a map M that satisfies this. This is what we call a mixed state. And if this X is equal to something isomorphic to like the identity, then you have that this is in fact a pure state. In fact, you can do this in F-Hilb and everything just works exactly as you would expect. Okay. So completely positive maps. Let's just see where we're at here. Okay, so completely positive maps. So we have that in a monoidal Dagger category, given two Frobenius structures, A and B. A positive map is a morphism A to B such that the composition, so that is to say this composition is mixed whenever this is also mixed. So more or less just that we want this positive map to preserve the mixedness of our two preparations. So also note that F going from A to B is positive, and so more or less what we also want is, it turns out that positivity on its own is not quite enough. We actually want something a little bit stronger, which is complete positivity. That is, if we know that some morphism F is positive, then what we would like is for F tensored with the identity, where on E is some other is any other, in fact, Frobenius structure with a different sort of monoid comonoid, then we also want this to be a, well, I guess, well, we want this thing to also be positive. Because in principle, if we don't do anything to the third system, or yes, the third system, then we would also expect for this to be a valid physical map. So let's try and encode this into something. So in a symmetric monoidal dagger category, given two Frobenius structures A and B, and a completely positive map, is a morphism from A to B such that this morphism is positive for any ancillary or auxiliary Frobenius structure E that's also in our category. So I wrote here that this is CP, but I should also say that more explicitly, this is complete positivity, because I don't want that to be confused with the CP condition coming next. So the CP condition is just particularly this diagram. Of course, we have that A and B, and all of these objects here are actually Frobenius structures. So the CP condition is any morphism F between A and B that satisfies this condition right here. So this is the CP. And now there's, in fact, a theorem due to Seinstring, and we're adapting it to this more abstract case, that the following are equivalent. If F is completely positive, meaning that it satisfies this condition, then it also satisfies the CP condition, which is this right here. Moreover, there's this third condition, F tensor IDE, which is positive for all objects X, where E, the third Frobenius structure, is given by this canonical X star tensor X and pair of pants and cap. So there's a couple of additional things that we can do here. Let's just check this. Okay. Okay, so there's a couple of additional results. CP maps compose, that is to say, of course, A and B, B and C all have some sort of Frobenius structure on them, and we're working in an appropriately defined category. If A and B, if F is a CP map and G is a CP map, then so is, or rather, sorry, yes, if it satisfies the CP condition, then so too does its composition. Now, in addition to this, in a braided monoidal category, for Frobenius structure, let's consider 4 Frobenius structures, I equals 1, 2, 3, 4. I didn't want to draw different colors here. So if we have that A1 is a CP condition satisfying map, F from A1 to A2, and from A3 to A4, we also have a map that satisfies CP condition, then so does the tensor of these, which is precisely what we want. So the CP construction is going to be as follows. Given a monoidal category, there's a category CPC in which, one, we have that objects are special symmetric Frobenius structures in C. This is essentially coming down to the notion that our objects should be something like this in order to capture the positive matrices. And the morphisms are morphisms of C satisfying the CP condition. So if C is a braided monoidal category, then C. So more or less the idea is as follows, that if you have C and you have that there's it's a monoidal category and you have these Frobenius structures in C, then you can construct CP of C, and the morphisms are morphisms of C satisfying CP. In addition, this construction satisfies all the sort of properties that you would like. For example, it plays nicely with the monoidal product. So if C is a braided monoidal category, then CP of C is also a monoidal category in which the tensor is well defined. There's a construction in chapter 4 of Vicary Heunen. Tensors of morphisms are also valid morphisms via the lemma that I had up here. Tensor is well defined. Okay, sorry. We have the appropriate unit and additional structures such as, let me actually make that very clear, alpha, rho, lambda, etc. These are inherited from C. Okay, in fact, let's use this medium for a second here to just go through. There's a sequence of results here that sort of just tell us that this CP construction actually sort of recaptures a lot of the constructions of F-Hild that we started with. So, for example, given a monoidal Dagger category C, there's a category CP. Okay, we just said that. The proposition 7.22 tells us that it plays well with the monoidal structure. 7.23 tells us that it preserves symmetric monoidal structure. Sorry, 7.22. Yes, that's correct. We also, in 7.24, that there's a notion of dual in CPC. CP preserves daggers in the sense that if C is a ribbon dagger category with trivial twist, then CPC is a dagger category. And also CP preserves dagger compactness. So if C is a dagger compact category, then so is CP of C. And also, okay, I think that those are the major things that I was going to say here. Okay, any questions so far? Let me check the Zoom. Okay.
Sorry,
Well,
I have a question about the term braided.
which one?
When you can you elaborate more about the definition of braided category?
The braided category. The braided category is going to be coming from something that we talked about earlier. More or less, the idea is as follows: that it's something weaker than the symmetric monoidal category. You have these. So let me see if I can come up with a picture. It's just one moment here. Yeah, so the braiding is as follows. So we have this ability to twist. So
Okay, okay.
braiding is something like this.
Okay.
It tells us that there's a morphism between a tensor B and B tensor A.
Okay, okay. I also have another question. In your definition of the Frobenius structure, the first step
Mm-hmm.
that you did was tensor identity. Can you explain a little more?
Okay, let me go back. So which part was this?
In the definition, when you
The definition of what? Sorry, I just didn't
the
catch it.
of Frobenius structure, the first.
Oh, the definition of the Frobenius structure. I didn't go through it because that was part of a previous talk, but I can go over it very quickly, which is as follows: that if I have just graphically something like uh, a monoidal sort of structure, which is this and this. So these are diagrams. So there's additional sort of coherence equations. These have to play nice with each other. So I'm gonna just not write those down. But then I also have maybe with a different color and like this. The Frobenius structure are two structures like this and this. In the physics lingo, this is like something like you're deleting, and then this is something like you are copying. And so I might have these the other way around. I have to think about that. But when these play together nicely, they satisfy a Frobenius law. Let's see. So to avoid, so if I go here, so if I have something that uh, satisfies a law like this, then you say that it's a Frobenius structure. Basically, you have a comoid, monoid, and a monoid working together that satisfies this, then you call it Frobenius.
Okay, okay. Mm, thanks. I see. Thanks.
Okay,
But
so maybe I can actually go through this argument once again then. So uh, the argument is as follows: that so say we have a monoidal category that has a duality in it, then this object here in our category actually has a canonical monoid structure, because what you can see is that I have the object A star A and A star A, and I'm deleting them. I have something that looks like this, and I have something that looks like this. So this is like a monoid. Then, if in addition I'm working with a monoidal dagger category, that allows me to actually flip things around. And so I also have the opposite of that. So now I have a comonoid structure, and because of the way it works with a dagger, this actually becomes a Frobenius structure. So I go from this to actually having something like an actual, you know, Frobenius structure. So that's that step. And of course, these are precisely the objects that are showing up in our definition of positive matrices. So that's kind of why these are. It's nice that we have this canonical monoid structure here. So if we want to talk about mixed states, we started with going from I to A. This is corresponding to some vector in Hilbert space H. Then we went from going from I to A, we went to A, which is something like A dagger, something like this. So, and then we actually made the switch from there to preparing positive matrices in this sense. So this is like preparing a mixed state. And then we can actually talk about maps between these objects, which ultimately gets to just defining um, a mixed state in terms of Frobenius structures that satisfy this equation here.
Thanks. Actually, a very nice talk. Thanks.
Okay, thank you. Yeah, so I think that I did something a little bit lazy, which was just I went through the notes instead of handwriting them. So I'm done like 10 minutes earlier than I would have liked to have been, or that I thought I was going to be. So if you guys have additional questions, feel free to pepper me and ask some more, or, let me see if there's any. Okay, it appears not. So I want to thank everybody for showing up. Please let me, if you have any additional questions, please let me know. I'll stay on for a couple more minutes, but if not, have a good weekend.